Hello, welcome to another module in this massive open online course. In this module, let us start looking at another very important topic in linear algebra, and that is of the least squares solution. Alright, so this is another very important concept that has significant implications. This is what is called as the least squares, is often abbreviated simply as the LS for least squares. This is known as the least squares solution. Now, to understand this, consider the system of linear equations let us say we have this system of linear equations y1, y2 up to ym. This is equal to the matrix A. Let us write this as the matrix A times x1, x2, xn. This is our system of linear equations where A is naturally an m cross n matrix, right. So, A is, so you have this, you can write this as y bar equal to A x bar, where y bar is m cross 1 vector, x bar is n cross 1, and A therefore naturally, which maps from the n cross 1 vector x bar to the m cross 1 vector y bar. This is the m cross, this is an m cross n matrix. Now, point here is, we have seen if m equal to n and A is invertible, right. If m equals to n, that is A is a square matrix, right. A is a square matrix, only then you can talk about the inverse, but even then it is not guaranteed, right. Any square matrix need not be invertible, right. Only if A is not singular, that is A is invertible, A inverse exists, right. Then the solution is given as, then the solution is, we have x bar equal to A inverse y bar. This is the solution if A is invertible, right, only if A is invertible. But however, now you see, now you see in this system, if you look at this, what is m equal to number of equations or number of observations, right. So, m equal to number of equations. You can also think of this in a practical system as the number of outputs, right. That is what this is in your wireless communication system. These are the number of outputs or observations. And what is x? These are the number of unknowns, right, or the number of transmit symbols, or the number of inputs, in your practical MIMO, multiple input multiple output wireless communication system that we have seen before, x1, x2, xn, these are the transmit symbols. Now, if m is greater than n, then there are more equations. However, m is strictly greater than n, then there are more equations than unknowns, more equations than unknowns, that is number of observations greater than number of outputs greater than the number of inputs. Speaking in terms of a linear system as an input output system, number of outputs is greater than the number of inputs. In such a situation, we call this is known as an overdetermined system. This is termed as an overdetermined system. This is termed as an overdetermined system. All right, such a system or such a system of linear equations where the number of equations m, that is the dimension of y, is greater than the number of unknowns n, right, that is the dimension of x. This is known as an overdetermined system. Now, what can we do? No, naturally m is greater than n, a is not square. This implies that, of course, invertibility of a is out of the question, because invertibility only, we talk about invertibility only if a is a square matrix, and that too if a is not singular, right. So, now how do you solve this system? So, what is the solution? So, what then is x bar, or how do you determine x bar? First of all, can you determine x bar? I think that is a more important question. The first thing you are, even before how to determine x bar, I think the more relevant question is, can you determine x bar? Does an x bar exist which satisfies this? That is an important question. And you will see, if you look at that system again, consider this y bar equal to, you write this in terms of this columns a1 bar, a2 bar up to an bar. This has n columns, each of size m, times x bar, which is x1, x2, x. So, this is essentially what this says is a1 bar x1 plus a2 bar x2 plus an bar xn. This spans, if you look at this, this is a linear combination. So, this has, if you look at this has basically n columns, right. So, if you look at this has n columns, implies this lies in, this spans, because this is a linear combination of a1 bar, a2 bar. So, this is a linear combination. Implies this spans an n dimensional subspace, right, implies Ax bar spans an n dimensional subspace. This spans an n at most, right, if the columns are linearly independent. But let us say, for simplicity, let us assume that A is full rank. The maximum rank is, because m greater than n, maximum rank is n. Spans an n dimensional subspace. But observe that, however, y bar belongs to an m dimensional space. it can be any vector in an m dimensional space implies. So, if you look at this n dimensional subspace, if you call this as CA, that is the column space spanned by the columns of A, that is right. If you call this as CA, what is CA? CA equal to column space of A which is n dimensional. Now, solution exists. Now, it is easy to see when does the solution exist. Solution exists only if this y bar, which can lie general anywhere in this m dimensional space, the solution exists only if y bar belongs to this n dimensional subspace, that is the column space of A. Otherwise, the solution does not exist. So, the solution exists only if y bar belongs to the column space of A. Solution exists only if y bar belongs to the column space of A. Otherwise, solution does not. Else, this has no solution. Exists only if y bar belongs to the column space of A. Else, if y bar does not belong to the column space of A, then solution does not exist. Then the solution does not exist. That is, you cannot determine an x bar which satisfies the condition y bar equal to A x bar, because any A x bar has to lie in the span of the columns of A and y bar lies outside this n dimensional subspace, right. Now, therefore, if you cannot determine a y bar, then what is the best thing? What is the best? Now, you can ask the question, as in engineer in particular, we do not give up when we cannot find an exact solution, right, because we are not, right. So, what is, because we do not give up, what is the best? Many times in life we cannot find the exact solution. What is the best that now we would like to ask? Fine, you cannot find the exact solution y bar equal to x bar. That does not mean that you have to give up. What is the best that you can do? And the best that you can do is find an x bar such that y bar is approximately equal to A x bar, right. So, now you change. So, now you change from exact to y bar is approximately equal to A. So, the point is, problem is it's a novel concept. If you cannot determine an exact solution, determine an approximate solution. And we want to find the best approximation. Remember, naturally as engineers and smart people in general, we would like to determine the approximate, I mean any solution is an approximate solution, right. I mean you can give x bar equal to 0 0, the all 0 vector, right, or you just randomly generate a vector, but we would like to find the best possible approximation. Therein lies the ingenuity, right. So, therefore, now we would like to find the approximate solution, but what do we mean by approximate solution? We would like to qualify this, we would like to find the best possible approximation. Not any approximation, but the best possible approximation. What do we mean by the best possible approximation? That is, if you look at y bar minus A x bar and call that as E bar, that is, this is the approximation error. This is the approximation error. Then we would like to minimize approximation error. But remember, this E bar is a vector, so I cannot minimize the approximation error. It does not make sense to say we are going to minimize a vector. We can minimize the norm of this vector, the length of this vector, right, or minimize the norm of the approximation error, which is essentially minimize norm of E bar. That is the problem that we want to formulate, which is essentially also basically similar to saying minimize the norm of E bar square. Which is equal to minimize E bar transpose E bar. So, we would like to minimize the norm of E bar square. That is, if you look at this quantity, that is nothing but norm of y bar minus h x bar square, minimize the norm of y bar minus h x bar square, and this is known as the least squares problem. Find the vector x bar such that the error y bar minus h x bar, if you look at the norm of the error and square of the norm of the error, that is the least. Therefore, this is known as the least squares problem. So, this is a very popular problem in entire signal processing, machine learning, data analysis, I mean whatever you look at it, and this is basically known as this is a very fundamental problem. This is essentially the least squares problem, which is essentially the title of our module. This is, in case you are wondering what is the least squares problem, this is the least squares problem, LS. And now we want to find the solution to this problem, that is the least squares solution. We want to ask the question, what is the least squares solution? Naturally, this is an optimization problem. So, let us first simplify the objective. So, minimize norm E bar square, this is basically minimize, let us first simplify the objective. So, E norm E bar square equal to E bar transpose E bar, which is equal to y bar minus h x bar transpose y bar minus h x bar, which is equal to y bar minus x bar transpose h transpose y bar minus h x bar, which is equal to y bar transpose y bar minus x bar transpose h transpose y bar minus y bar transpose h x bar minus x bar transpose h transpose h into x bar. It's a very straightforward simplification. Now, if you look at this, note that these two quantities, these two are the transpose of each other. These two are equal because they are the transpose of each other. So, this is, you can write this as y bar transpose y bar minus twice x bar transpose h transpose y bar, sorry, this is going to be a plus x bar transpose h transpose h x bar. So, this is essentially going to be the objective function, or this is the simplified version of the objective function. Now, we have to find the minimum. Now, we find the x bar, we have to find the x bar which minimizes this objective function, alright. So, essentially what we have is, this is basically your objective function. Find x bar which minimizes the objective. So, let us call this as f, alright. This is your f of x bar. Find the x bar which minimizes this objective function. The task is very simple. find x bar which minimizes f of x bar. And the way to do is a very straightforward procedure which is known as the KKT framework, the Karush-Kantukar. So, to minimize this is like an optimization problem which you are all familiar with f x bar. Compute the gradient with respect to x bar and set it equal to 0 to find what is known as the stationary point, or in this case it will of course be a minimum, right, because this is unbounded. You can clearly see, you can take this as close to infinity as possible. So, this is essentially going to be, when you find a stationary point, this is going to be a minima, right. So, you set the gradient equal to 0, this is known as the KKT framework, alright. Karush-Kantukar framework, a very standard framework in optimization, and it is very intuitive. Essentially for a scalar function, what you are doing is you are computing the derivative and setting it equal to 0, except now that x bar is a vector. So, you have to compute the partial derivative with respect to each component of x1, set it equal to 0. Okay. So, that is what this is. If you look at this, this implies that delta f x bar is nothing but the vector of partial with respect to x1, partial with respect to x2, partial with respect to xn, each component of x, and this is equal to 0, which basically implies that you are setting the partial with respect to every component of x, partial with respect to the derivative with respect to every component of x is equal to 0. Derivative at the optimum point, derivative with respect to every component of x bar is equal to 0. Let us see how to do this. Let us look at some properties of the gradient. Properties of the gradient operator. If you have a constant vector c bar transpose x bar and you take the gradient of this, that is, if you look at the gradient of c1 x1 plus c2 x2 plus cn xn, you can see this is nothing but this is essentially given by the vector gradient with respect to x1, that is equal to c1, gradient with respect to x2 is c2. So, this is c bar, which is essentially c bar, and this is also gradient of x bar transpose c bar, right, x bar transpose c bar or c bar transpose x bar, both these quantities are the same, because c bar transpose x bar equal to x bar transpose c bar. The gradient with respect to is a very simple linear function, right. So, the gradient with respect to x bar is c bar, and now if you look at a quadratic function, the gradient with respect to, for instance, x bar transpose p x bar, this is a quadratic function, you can show that this is equal to p plus p transpose x bar, which is equal to twice p x bar if p is a symmetric matrix, that is p equal to p transpose, okay, p equal to p transpose, that which implies basically that p is a symmetric matrix. Okay. Let us come back now to our objective function. Now, let us use these properties. So, this is what we are calling as a linear. Now, if you look at this, essentially these two things are essentially what you are calling as linear objectives or the linear components, and this is the quadratic second order term. And in fact, if you look at our objective function f of x bar, you will notice something interesting, this is essentially equal to, what is this equal to? This is essentially equal to y bar transpose y bar minus twice x bar transpose h transpose y bar, I am sorry, h bar transpose, I am sorry, this has to be, I think at some point we missed, that is fine. I think we can continue with this h, where we have now the notation in terms of h. It is okay, let me just change this probably to a y bar minus a x bar everywhere, and this also here has to be a, this has to be a transpose, this has to be a, this has to be a transpose, this has to be a, and this has to be a transpose a, this has to be a transpose, this has to be a transpose a, and this is therefore, if you look at it, 2 x bar transpose a transpose y bar plus x bar transpose a transpose a x bar. And if you look at this now, if you look at this now, essentially what you are going to see is that this is basically a quadratic, that is, if you look at this, so this is basically, this is a constant. Let us now dissect this. This is a constant, does not depend on x bar. This is your linear term, and this is basically your quadratic term, second order term. So, overall this is a quadratic expression. Okay. And therefore, now if you find the gradient of this, that is gradient of f of x bar, that is equal to, the constant term gradient will be 0 minus twice x bar transpose c bar. So, the gradient c bar is A transpose y bar. So, this is A transpose y bar plus this is x bar transpose p x bar, where you can see p is symmetric because A transpose A is equal to its transpose, that is A transpose because, so this will be twice A transpose A x bar, which are setting 0, and this arises because A transpose A transpose is nothing but A transpose A. It is basically, you can easily see that A transpose A transpose A is symmetric, and this implies that setting it equal to 0 implies that A transpose A, of course the 2's cancel. So, A transpose A x bar equal to A transpose y bar, and this implies the x bar, which is the solution to this, is equal to A transpose A inverse A transpose y bar. This is basically your least squares solution. Okay. So, this is A transpose A inverse. This is a very interesting solution, and of course, here we are assuming that A transpose A is invertible. If A transpose A is invertible, which is not very difficult to show that this exists, it can be shown that A transpose, which holds if A transpose A is invertible. Remember, this holds if A transpose A is invertible, which is true, this is true if A, we will not prove this explicitly, is full column rank, which is, that is, this implies that rank of A is equal to n, right? A transpose A is invertible whenever the rank, this is a full column rank, it has rank equal to the number of columns, that is rank of A equal to n number of columns. Okay. Now, this is a very interesting solution. Let us look at this solution. This is a very interesting solution. We have the least square solution. This is, in fact, this is termed as the least square solution. The problem is the least squares problem, A transpose A inverse A transpose y bar, and this is essentially termed the, what is known as the, this is essentially termed the least square solution. This is essentially termed the least square solution, or basically, as you also know, we call the least squares abbreviated as LS. So, this is basically termed as the LS solution, all right. And A transpose A, this matrix is an interesting structure. So, if you look at this matrix, which is this A transpose A inverse A transpose, this has a very important meaning. This is termed as the pseudo-inverse. This is the pseudo-inverse of A, right, this A transpose A inverse, and this is often denoted by A dagger. This is what is termed as the dagger. This is denoted by A, this is A transpose A inverse into A transpose, this is the pseudo inverse of A. Now, this is termed a pseudo inverse because this has a very interesting property, because now remember, if m greater than n, A is not invertible, but if you look at this matrix, multiply it with A on the left, A transpose A inverse A transpose times A, this is equal to A transpose A inverse A transpose A, which is A transpose A inverse into A transpose A, this is identity. So, this acts as an inverse, more specifically it acts as a left inverse of A, hence it's termed a pseudo inverse. So, if m is greater than n, strictly speaking A is not invertible, but this matrix is acting, right, it is appearing as if it is an inverse of A, but it is not really an inverse of A, you can clearly see, because it does not satisfy any properties of the inverse. For one, if you multiply it on the right, any inverse, if AB is square matrix is invertible, if AB is identity, then BA also has to be identity, right. But if you multiply this on the right, you will not get the identity, right. So, in fact, that is a very interesting property that we will look at subsequently. So, this is only a pseudo inverse because it appears to be like an inverse, it acts like an inverse, right. So, this quantity essentially acts like an inverse. That is why this is termed as a pseudo inverse, right. So, this quantity acts like an inverse, it is not an inverse, it acts like an inverse, okay. Because note that A is not invertible if m is greater than n. This is always important to remember, because if m is greater than n, A is not a square matrix, because if m is greater than n, A is not square. In fact, if you look at A, this is an interesting structure. If m is greater than n, it looks something like this. It has more rows, more height than width, more rows than columns. This is often termed, it looks very slender, and tall. This is often termed in colloquially in linear algebra, is often termed as a tall matrix. In engineering and linear algebra, this is often known as a tall matrix because it looks like a tall matrix, more rows than columns. So, implies this is often termed as a tall matrix, alright. This is some, take it with a pinch of humor, alright. This is not something that you use in a formal paper, but this is something that is termed as a tall matrix. And also because it only gives the identity when it is multiplied on the left, you note that A transpose A inverse A transpose into A is identity, that is it is multiplied on the left, gives identity when multiplied on left, implies this is termed as a left inverse, because on the right it does not give, this is a left inverse of A. And in case you are more interested, another interesting fact that you will also realize that this left inverse of A is not unique. If m is greater than n, left inverse is not unique, the pseudo inverse is one of the left inverses. Okay. So, there might be some confusion, especially if you are seeing for this for the first time, because there is an inverse and there is a pseudo inverse, but it is very simple. The pseudo inverse, as the name implies, is not an inverse. If m is greater than n, then this is only a pseudo inverse. Now, the interesting point is, if m equal to n and A is invertible, pseudo inverse reduces to the inverse. For square matrices, again you might be confused which one to use, should I use the pseudo inverse or should I use the inverse, does not matter. Square matrix, if the inverse exists, pseudo inverse equals the inverse, and that you can see also in a straightforward fashion from this equation. Alright. So, it is a very interesting concept, a very powerful, very important concept, arises everywhere: signal processing, machine learning, engineering, communication, and all fields of engineering. In fact, there is hardly any field of science, engineering, probably business, management, even probably economics, right. Wherever you have data, wherever you analyze data, wherever you are fitting data, I mean anywhere, probably even in politics, wherever you have data and you are trying to fit data, this is the problem that always arises, and we are going to see several applications. One of the most important, profound and fundamental applications, I would say, in entire linear algebra. Alright, so let us stop here. Please go through this once again to understand this thoroughly. Thank you very much.